Once again, welcome to my YouTube channel called Pearson and Excel International Maths by Mr. Kamotho. And today I'll be explaining example 1 in topic 5, that is on page 103. Having said that, it is important that we note that we have introduced the first video in this topic that was introducing entirely what we have or what we expect in this topic. And in example 1, we are told that let's have example 1 here. Let's have example 1, and we are told that on the same axis, sketch the graph of y is equals to 3 raised to power x, y is equals 2 raised to power x, and y is equals to 1.5 raised to power x. And then we will be looking at part B. But I would want to say something about these graphs that we have seen. Let me just explain something here. We have seen that all exponential graphs, they will pass point 0, 1. Why are we saying that? Because when 3 is raised to power 0, it is 1. When 2 is raised to power 0, it becomes 1. When 1.5 is raised to power 0, again, it is 1. But let us think when x is a negative number. And let us just do something here. And let's talk about when x is a negative 3. When x is a negative 3, let's talk of what is 3 raised to power x? What is 2 raised to power x? What is 1.5 raised to power x? When x is a negative 3, so to speak, just a general picture of what it will look like. We are going to have 3 raised to power negative 3. And this is basically 1 over 3 raised to power 3, which is 1 out of 27. When x is negative 3 and 2 raised to power negative 3 is going to be 1 over 2 raised to power 3, which is basically 1 out of 8. And then when x is negative 3, of course, when we are talking of 1.5, it's going to be something to do with 1 over 1.5 raised to power 3, which is 1 over 3 point, let's say 4, because it's 3.375. I want you to look to compare the three values and note that 1 over 27 is smaller than 1 over 8, which is far smaller than 1 over 3.8. So among the three, 1 over 3.8 is the highest. So let's just talk about categorizing these graphs, and let's talk about 1.34 will pass there. And obviously, when x is, let's say, negative 3, you expect the graph of 1 over 27 to be there. And 1 over 8 is in the middle. Let's talk about it being there. But when we get to this particular point, all of them meet there. Let's say when x now is a 3, positive 3. 3 raised to power positive 3 is 27. 2 raised to power positive is 8. And 3 raised to power 1.5 raised to power 3 is 3.4. So again now, you will see that 27 is far much bigger than 8 and far much bigger than 3 point. So when x is now a positive 3, the graph which was the smallest here, which was 1 over 27, it's now the greatest there. When x is now positive 3, the graph that was the highest here, it's now the smallest there. And of course, the graph that was in the middle there still remains in the middle. So we are going to talk about this graph passes through 0.01 as it moves to. So we are going to talk about this graph as 3 raised to power x. What about this other one, the second one? It's still passing through the 0.01, and now when it's crossed over to the positive values of x, it becomes smaller than that other one. So this one is now the graph of y is equals 2 raised to power x. But look, there's a graph here which again passes through the 0.01 but continues to be smaller when x crosses to the positive side. So I would want to highlight this one as y is equals to 1.5 raised to power x. So the three graphs is not this is not a straight line, but you would see after with time when this one continues to rise, this one continues to rise, and this one again continues to rise. But I wanted just to highlight that on the when x are negatives, the graph that looks small is the one that is going to be bigger there. And why? Let me explain using this table. It's because we are talking about when x is -3, 1/27, 1 divided by a very big number is of course a very small number. When x is -3, 1/3.375. 3.375 is not as big as 27, and 1 divided by a relatively smaller number, then the quotient is going to be relatively bigger. And that is why they have interchanged position, or they have interchanged the lead as far as the values are concerned. Immediately they cross over the y-axis. So that is the graph of these graphs have been plotted in the same set of axes, and that is just what we have. If we look at part B in the same kind of example, let's talk about part B in the same set of example. In the same example, part B is saying, on another set of axes, sketch the graph of y is equals to a half raised to power x and y is equals 2 raised to power x. And I want us to first of all get this first. Let's get this clearly, because this one is the graph that we started with when we were introducing this topic. So we have no issue with the graph of y is equals to 2 raised to power x. It's just passing through 1 there and continuing. This is the graph of y is equals 2 raised to power x. But it is the graph of half raised to power x that is going to be a bit of a problem. How? But let's see. When x, let's talk about x. When x is -3, and we are going to talk about a half raised to power -3. This one is the same as the reciprocal of the constants, because it's going to be 1 over a half raised to power 3. What does this mean? This is simply 2 raised to power 3, which is 8. And I want us to look at it this way. When y is a half raised to power x and x happens to be -3, x happens to be -3. So a half raised to power -3 is the same as 1 over a half raised to power 3. And when anything is divided by a fraction, we need to multiply by the reciprocal of the divisor. Meaning that now 1 over a half raised to power 3 is 2 over 1 raised to power 3. And this is simply now 2 raised to power 3. And it is what we are calling an 8. So when we are talking of when x is -3, so and the function is y is equals to a half raised to power negative 3, which is 1 over a half raised to power 3, because everything, when we are talking about 1 over, the sign of the index automatically reverses. So, and this one, 1 over a half, and I want us to just look at it here. 1 over a half is the same as 1 over 1 times the reciprocal of the divisor 2 over 1, which is 2. Now, 2 over 3 is what we are calling now an 8. That is exactly what has happened. So when x is probably negative 3, we have an 8. Our graph is up there. But let's see what happens when x is a 3. A half raised to power 3. A half raised to power 3, this is the same as a half times a half times a half, which is actually 1 over 8. And all the way it goes to 1 over 8. And it becomes, when x is 3, it becomes a very small number. But of course, when x was 0, it is a half raised to power 0, which is 1, and all the way equals to 1, because we said any number raised to power 0 is 1. So we are going to have a curve or a graph that looks like this. And this one is the graph of y is equals to a half raised to power x. Note the difference. This is the graph of 2 raised to power x, and this is the graph of a half raised to power x. As we move forward, we are going to see how this increases. And of course, it is also important to note, if I may also want to explain something like here, in a different format, I would say a half is by itself 2 raised to power negative 1. So when we are talking about 2 raised to power negative 1, if x was probably negative 3, 2 raised to power negative 1 raised to power negative 3, you multiply the power out, becomes 2 raised to power negative 1 times negative 3, which is 3, and is going to be 8. So again, that supports why we are having an 8 there. It is important that we all get to understand why the graph takes that shape. Again, yes, I have gone slowly in that example because I thought it is important that we understand. Please again go to my YouTube channel called Pearson and Excel International Maths by Mr. Kamotho. Subscribe, share, and like, and let us work together. All right?